Hey everyone, my name is OC, and today I'll be talking about the closest pair problem. Now, the closest pair problem is honestly one of my favorite divide and conquer problems because as a student, I didn't really understand and therefore appreciate how it worked. And now when I became an instructional aide or IA and I had to start learning how to teach it, I was like, oh, this is pretty cool. And so I'm hoping to kind of share that understanding with you, but also that excitement because it is really cool how it works. And so the problem of this, the closest pair problem, is we're trying to find the pair of points on a graph that are closest in distance. So for this particular graph, these 2 points are closest in distance. So we're trying to devise an algorithm that could find any 2 points that are closest in distance. Now, one naive way of doing it, and I think it's with two dots on the I, I'm not sure. One naive way of doing it is for every point on a graph, we compare it to every other point. And when we do that, we then take the smallest distance that we find when we do that and then return that. And that works. That is perfectly correct. However, it's pretty slow because for every single point, we have to compare it to every other point, which makes it O of n squared if we have n points. And that's pretty slow, especially if a lot of points. Like imagine if we had hundreds of thousands of points. That's kind of bad. So what we're going to try to do is use divide and conquer to make our runtime better. In particular, we're going to make it O of n log n. So how are we going to do this? Well, remember, there are two parts to divide and conquer. There's divide and there's conquer. So we're going to focus on the divide part. The first thing we're going to do is, I mean, not to do that. The first thing we're going to do is we're going to divide our graph in half. All right. We're going to divide it in half so the left side has 50% of all the points and the right side has 50% of all the points. Well, we have a statistical tool that can do that. That's called the median, where 50% are below, 50% are above. So what we're going to do is we're going to find the median and draw that line in our graph. It might not be in the middle. It might be skewed otherwise, but for the sake of clarity, I'm going to put it in the middle. We're going to draw our median. We're going to get a median and draw that line in our graph such that 50% of the points are to our left, 50% of our points are to our right. And even honestly, for clarity, I might even move this so you don't think I'm doing. Actually, I'll keep that there. But we're making sure that 50% of the points are to our left and 50% of our points are to our right. Now, for those who are, I was like, how do we find the median? There are actually algorithms out there that can do an O of n time, or you can pre-sort it beforehand as well. Just believe me when I say that finding the median won't affect our runtime. And if you want more understanding, please do your research on your own. But it won't affect our runtime of this algorithm. So, like we said, we're doing divide and conquer, and we divided our graph into two halves. One that has 50%, other one has 50%. Now, when we're considering the pair of points that have the closest distance, there are now three possible locations where those pair of points could be, right? Both could be I keep moving it. Both could be on the left side. Both, like as these two right here are. Both could be on the right side, or one of them could be on the left, one of them could be on the right. So there are three possible cases, and we have to consider all three possible cases. So what I'm going to do is I'm going to do as follows. I'm going to say, hey, what I want you to do, and I'm going to do this recursively, or that's the divide part. I'm going to do this recursively. Give me the smallest distance from the left side. All right, give me the smallest distance from the left side. So I'm going to call my function recursively on all the points on my left side. And I'm going to say, hey, give me the smallest distance you found from this left side. So I'm going to call that left of S. So the smallest distance on the left side. And remember, this is going to be a recursive call. So closest pair, I'm going to say left. And I want you to find, likewise, the smallest distance from all the points on the right side. And again, that's going to be done recursively. So R of S, the shortest distance on the right, is our recursive call on the right side. Now, remember, this returns the smallest distance on either side, so the left or the right. What we care about, though, is the smallest distance between any of the points. So we have the ones from the left, ones from the right, and now we have to consider the middle. So when we consider the middle is the case that makes this algorithm, in my opinion, special. Why it's actually super, super cool. So what I'm going to do is say, hey, when I'm considering the middle, I don't want to compare it to either left or the right. I just want the minimum of the left or the right. And then whatever the minimum is, I'll use that as my basis of comparison for any points I consider when I'm comparing the left to the right. All right, so what I'm going to do is saying, hey, give me the minimum of left of S and the right of S. This is the smallest distance I have to consider because whichever one is going to return this is going to return the minimum of those two. And when I'm comparing points from the left and the right, I just have to, whenever I calculate a distance, all I have to do is compare that to this minimum. I'm going to call this minimum alpha. You might see it in other places. It's called gamma. I don't know how to draw gamma that well, and I don't care to draw gamma that well, so I'm just going to call it alpha. It doesn't really matter. So we're going to call this minimum distance alpha. And now we want to consider, remember, we have three possible cases, both on left, both on right, or one on left, one on right. So now we have to consider that third case. Now, how should we approach that? Well, again, one naive way of doing so is we compare every single point we possibly can. So for every point on the left, we compare that to every point on the right. We calculate those distances, and if it's smaller than our alpha, great. That's our new minimum. Now, you may already know this is pretty bad. This will get us to O of n squared again, and that's not fun. So let's try to reduce the number of points we have to consider. All right, instead of trying to figure out a new way to do all the points, let's see if we can reduce the number of points we have to consider. Well, one key understanding that we can get is that let's say we drew a line from the median and we had that alpha distance away. All right. We had this imaginary line that's alpha distance away from the median. Well, what's really cool is that any point that lies outside of that line, of that alpha line, when we compare to any point on the right side, we're guaranteed that that distance is at minimum alpha. Why? Because that distance already is alpha away from the median, and if there's anything on the right side, it's guaranteed to be either on the median line or farther. So the distance from our left side to anything on the right is at minimum going to be alpha. So there's no need to consider any points that are alpha distance away from the median because they're guaranteed to be at least alpha farther from any point on the opposite side. So what we can do instead is we can draw this box. Draw this box. They call it a strip. I say they, like the mathematicians you read in your book. They call it this strip. They call it the alpha strip. So they draw this box, and what's neat about this box is that it is 2 alpha in size. All right, so it's alpha in the left direction, alpha in the right direction. Any point that lies within this box, within this strip, those are the only points we have to consider when we're trying to compare anything from the left to the right for that third base case that we talked about. So now, does this actually help us? So now we've created this 2 alpha box, and because we did that before, because again, we don't have to consider any points from the outside. And so now what should we do? We're trying to find the smallest distance within this box. What's an approach? How could we do this? Well, again, one naive way is that we compare every point that's in this box with every other point in this box. You already see right now that we've greatly reduced our subset of points, so maybe this would work. The problem is this naive approach wouldn't. And the reason is because there are some cases of graphs in which every point in our graph actually lies within this strip that we created. One such case is that let's say every point was on the edge and each point was alpha distance away. Well, this would work. We would still have alpha and this would still work. And if we compared every point with every other point in that box, well, we would have to do O of n squared computations in the end, and that's not fun at all. So unfortunately, even though it's a rare case, because it doesn't look like that's actually that possible, it's a rare case, yeah, but we care about worst case runtime. And unfortunately, that is a pretty bad runtime. So what could we do to try to eliminate these worst cases, these cases that make it O of n squared if we did that naive algorithm? Well, let's look at triangles for a second. I know it's a weird thing to say, but let's look at triangles for a second. When we have a right triangle, right? I mean, this is X, Y, and H. I say X, Y, and H on purpose. We know with any right triangle that our hypotenuse is greater than both sides in terms of length. So our hypotenuse is always greater than both sides. So that means, and this is just a fundamental understanding of triangles. That means that if we're comparing 2 points, for example, let's compare these 2 points right here. That means that if their distance in the y direction is greater than alpha, so their y direction right here, if their y is greater than alpha, that means their distance, I'll do orange, their distance also has to be greater than alpha. Why? Because that distance is going to be their hypotenuse if we created a right triangle between them. So we know for a fact that if any point, 2 points, oh, what did I do? Any points, at any point, there are 2 points whose y distance is greater than alpha, then their overall distance has to be greater than alpha. Has to be greater than alpha. So how could we use this understanding to help us limit the number of points we have to consider? Well, what we can do using understanding is that for every single point in our box, we create another one. So let's say we're considering this box. We create another, we're considering that point. We create another box that's alpha in length, like this. So we basically create a box that's 2 alpha by alpha. And the only thing we do with regards to this point, we only compare and calculate the distances to any point that lies within this box. So for this particular point, this is the only point that lies within that box, like basically. So we compare it to only that one. So we don't compare it to this. We don't compare it to that. We don't compare it to that. We only consider the points that are in that box and only that box. So if we, to extrapolate that further, if we were considering this point right here, we would create a box that's alpha in length and by 2 alpha, and therefore we'd only compare and calculate distances to these 2 points here. Only 2 points we consider. Now, again, this works because remember, if there's any point that lies outside of this alpha box, this a new box that we created, that means it's at minimum alpha distance away in the y direction. And if it's alpha distance away in the y direction, their distance has to be at least alpha, if not more. So what's really cool about this box that we created is that the number of points, therefore, you're going to compare to at max, 7. The number of points you're going to compare to at max for any given point, the number of points that could be actually in this box is 7. Isn't that weird to say? Just a constant number 7? That's just insane. And why? The proof for this, I'm going to leave to you as an exercise. All right, I'm going to leave this to you as an exercise. My suggestion, proof by contradiction. So if the max number of comparisons we can make is 7, that means the max number of points that we could have in this 2 alpha by alpha box is 8. Proof by contradiction, what would happen if we had more than 8 points in this box? That's my question to you. So now, because we have a constant number of comparisons, we do this for every single point in our alpha strip, our 2 alpha strip. So for every single point, for every single point, we do that constant number of comparisons, and the max number of points that we could have in our strip, as we previously mentioned, was n. So for n elements, we do a constant number of comparisons. This makes that part of checking the middle. This makes that O of n. So in the end, for our algorithm, our conquer step, that middle part is O of n. Now, referring to our overall algorithm, remember we had the 2 recursive strategies of left and right. We have our conquer part of O of n. And then we once we get all the distance, we get the smallest and return that. That's our algorithm. So we have left, we have right, get the minimum, calculate smallest in middle strip, which we already said to be O of n, return smallest. So this is, we're doing this, we're dividing our input in half. So this is T of n over 2. This is T of n over 2 because it's the exact same call with half the inputs. This is O of 1. And this, like you said, is O of n because we have n elements and we're doing a constant number of comparisons per element. Now, what's the runtime of this algorithm? Well, T of n is equal to 2T of n over 2 plus O of n. Run that through master theorem, you get O of n log n. So it's really, really cool. We converted an O of n squared strategy to an O of n log n strategy by using divide and conquer. And remember, the idea was we had 3 possible places in which our closest pair points could be, both in the left, both in the right, or one on the left, one in the right. So we got the smallest from the left using recursive strategy. We got the smallest on the right using recursive strategy. Now we have to figure out the middle. When we figured out the middle, we realized the only points we have to consider from the left and the right are those that are within alpha distance. Because if they're outside that alpha distance, they're going to have a distance greater than alpha. Likewise, within this strip that we created, we don't have to compare every single point that's within this strip. Because if their y distance is greater than alpha, that means their overall distance, because of how right triangles work, is going to be greater than alpha as well. So when we understood that, we realized that the number of comparisons or number of distances we're going to have to calculate per point in our strip is going to be a max of 7. So we have O of n elements times 7, a constant number of comparisons makes that O of n. And then once we calculate all the smallest distances, we do that for everything, we return our smallest, which is exactly what we want. And in the end, that becomes an O of n log n algorithm. So I hope you enjoyed this. Please try the strategy on your own. And also, one thing that could confuse you is how the recursive part would work. I want to urge you, what would be the base case for this? What would be the base case for this? And what would you return in the base case? What's the smallest distance in terms of the base case? Or what would you algorithmically, what would you try to return in terms of the smallest, in terms of the base case? And how would you approach the base case? But yeah, that's it for closest pair. It's one of my favorite algorithms. It's really, really cool. I love teaching it. I love talking about it because I think it's a really, really smart strategy. And it takes a lot of intuition about how triangles work or what we could deduce and how that could help us reduce our problem and increase or decrease our runtime. So, like I said, my name is OC. Thank you so much for watching. If you have any questions, let me know. Yeah, have a great rest of your day.